see I cannot see any attendees now. Okay, now they're coming. Okay, let's wait a minute or two. Okay. Good afternoon from Vienna, everybody, and welcome to today's webinar of the Win for Peace group. Today we are going to speak about the important topic of small modular reactors, which everybody's talking about. And in particular, we are going to look at how to safeguard such reactor types. Before giving our two speakers the opportunity to speak, I would first of all like to introduce you to the Win for Peace group, to tell you who we are and what we do. And maybe you will get interested in our activities. So let me briefly present our program. So the Win for Peace group is a group of expertise within the Win Global umbrella that was founded about a year ago. And we strive to contribute towards world peace through the involvement of more women in the areas of nuclear non-proliferation, safeguards, export controls, and disarmament. And we conduct coordinated activities across all 4 domains, in particular in education and training, through webinars and hybrid events. My motivation for establishing the Win for Peace group was because I strongly believe that we need more women involved in the Win for Peace subject areas in order to contribute towards world peace. Membership in our group is open to all Win Global members, and we currently have 20 members from 4 continents, and I'm the leader of the Win for Peace group. And here is a picture of our 20 members. And we also have 2 supporters. One is the Vienna Center for Disarmament and Non-Proliferation, the VCDNP, and the other one is the UN Office for Disarmament Affairs, the UNODA at Vienna. In 2023, we conducted 7 webinars on different topics. First of all, the basics of the non-proliferation regime, safeguards basics, and national, regional, and international implementation experiences. We also spoke about Iran's nuclear program, about the basics of nuclear export controls, the AQ Khan network. We looked at the status of nuclear disarmament, and we spoke about nuclear propulsion, and in particular about the AUKUS project. We had 555 registered participants and 355 unique viewers. And you can find the recordings of our webinars on our YouTube channel. So you just need to Google Win Global, and once you see the logo, you will see all the recordings of our webinars. In 2024, we also plan a number of webinars. So we already had the first one on the basics of nuclear weapons with Bob Kelly. So today is our second webinar on safeguarding SMRs with Adjoa Amponsah and Jeremy Whitlock. On the 8th of April, I will give an overview of the nuclear fuel cycle upon demand of our members. Then on the 6th of May, we will have Rhonda Evans from WINS, from the World Institute of Nuclear Security, who will speak to us about the activities of WINS and cybersecurity at nuclear facilities. On the 10th of June, our member Nusa Ben Rais from Morocco will give us an introduction to nuclear physics basics. Sometimes either in July or later, we will have a talk from somebody from the CTBTO about the CTBT, the Comprehensive Test Ban Treaty. Then in August, Susie Snyder from ICANN will talk about the TPNW, its current status and implementation. And we plan to have 2 sessions on nuclear weapons-free zones. The announcements for our webinars are published on social media, on like Facebook, LinkedIn, Instagram, and also by email if we know your email address. And everyone is free to participate. So without further ado, let me now introduce our 2 speakers. So we will have 2 speakers for the webinar today. One is our young member, Adjoa Amphontvi. Adjoa has just completed her internship with the IAEA in the nuclear power technology development section. She's also a recipient of the IAEA Marie Sklodowskaya-Curie Fellowship and a member of the INMM, the Institute of Nuclear Materials Management. Adjoa has acquired substantial knowledge and training experience in non-proliferation safeguards and disarmament, and recently in reactor operations. And she has also researched and published abstracts in conference proceedings on non-proliferation and safeguarding SMRs, and continues to follow up with more research. So that's our first speaker. And our second speaker will be Dr. Jeremy Whitlock. Jeremy is a senior technical advisor at the IAEA's Department of Safeguards. He has 3 decades experience as a scientist and manager in the Canadian and international nuclear community. And prior to moving to the IAEA in 2017, he spent 22 years at the Canadian Nuclear Laboratories at Chalk River as a reactor physicist and manager of non-proliferation R&D. Jeremy is also the past president, fellow, and former communications director of the Canadian Nuclear Society. Since 1997, he has maintained the Canadian Nuclear FAQ, and the location is www.nuclearfaq.ca. Maybe we will put it in the chat. Agostina, maybe you can put this link into the chat. It's a very interesting website. I checked it out this morning. So he has created this personal website of frequently asked questions on Canadian nuclear technology. And I find it very, very comprehensive. I encourage you all to visit it if you're interested in CANDO technology. And on a private note, Jeremy loves canoeing, and he feels that canoes are the closest humans have come to inventing a perfect machine. So I don't know how much canoeing you can do in Vienna, but certainly near Chalk River, there were a lot of opportunities. Before I hand over to Adjoa, I would like you to keep the questions till the end, and to put them into the Q&A section at the bottom of your screens. And after the presentations, we will then open the floor to your questions. So as you know, everybody speaks about SMRs nowadays, and there are, as far as to the latest count, there are about 100 different types of SMRs that are being developed worldwide. And these are both based on existing technologies, but also on new technologies like Generation 4 technologies. And you can imagine what a challenge that will be to the IAEA to develop new safeguards approaches for such new technologies. So this is what we will speak about today. And as you know, countries, as they develop their nuclear programs, they are also subject to the safeguards measures, because most countries have signed the NPT and brought into force a comprehensive safeguards agreement. So it's really important to consider the safeguards measures that need to be applied at those facilities. Adjoa will first highlight the importance of safeguards in SMRs, including safeguards by design, the manufacturing models and commissioning, and the associated challenges. She will also touch upon the potential synergies between optimal design solutions and nuclear material accountancy and control. And after that, Jeremy will summarize the IAEA challenges in the activities in preparing to support the state's safeguards obligations when they deploy SMRs. So, without further ado, Adjoa, the floor is yours. Please unmute and please share your presentation. Thank you.
Okay, I'm going to begin to share. Okay. Thank you so much for this opportunity to share this with such distinguished and well-achieved experts. In as much as I'm going to present on a snippet from my own research activities, I see this as a learning opportunity for me as well. And so my title for the presentation today is Safeguarding Small Modular Reactors, touch ups on their design and then their potential synergies. I'd also like to mention that this presentation is from a research work that I submitted to the past joint annual meeting between the Institute of Nuclear Materials Management and the European Safeguards Research and Development Association. The presentation will cover an overview of SMRs and then delve into the safeguarding issues and then the topics, the various topics. So there will be an overview, a brief background of proliferation risks related to SMRs, the challenges identified, safeguards by design. This particular one will be touched more on by Dr. Jeremy, so I wouldn't talk much about that. And then I'll end with potential synergies to be considered in this case. So starting with a short overview on SMRs, I'm sure by now everyone knows what SMRs are. And it is important to understand that nuclear energy offers a very compelling solution for addressing the growing energy needs with minimal environmental impact. And in that sense, small modular reactors have begun to come to the forefront as a potential solution to meet the world's growing energy demands. And this is because of a number of reasons. For one, currently the leading energy source in mitigating climate change issues have been named to be the renewable energy sources. But then it is very important to note that there is the need for a formidable backup energy for when weather conditions pose issues. For example, when it comes to solar energy, the energy cannot be captured during windy or rainy days or even during the night. And so during times like this, there is a need for a formidable backup energy where nuclear power comes in friendly. And nuclear power is both climate friendly, it's efficient, it's versatile in energy production and then cogeneration abilities. And small modular reactors have shown promise or show promise in providing a much safer and more efficient alternative to the larger traditional power reactors that has been used for decades now. And then due to their adaptability for remote areas, their smaller size, the flexibility and scalability, they present a very versatile, cost-effective solution to many energy scenarios across the world. So this picture that I put in here kind of summarizes why SMRs have become very important. I made mention of the fact that they are modular, which means that they can be assembled in a factory and then transported to the point of use. So as it's shown here, we can see the manufacturing factory here assembling the SMR units, and then it's being transported to the site of application. And then their flexibility, as you can see, they can be sited in very remote areas where large power plants wouldn't necessarily be that relevant to be. And they can be applied for cogeneration purposes, like as it has been shown here. Electricity is being produced from the reactors, and then it's also being coupled to other transformative energy processes like hydrogen production, desalination, and then the likes. Now, to talk about a brief background to safeguards, it is important to note that safeguarding nuclear technologies is very crucial. And this is because it helps to prevent the proliferation of nuclear weapons. And this ensures that nuclear materials are being used exclusively for peaceful purposes. And when we talk about nuclear proliferation, it basically refers to the spread of nuclear weapons, materials, technology to additional countries or non-state actors beyond the existing nuclear armed states recognized under the NPT. And it basically consists of acquiring and developing or transferring nuclear weapons or just having the capacity to produce them. And this whole situation could lead to catastrophic environmental and humanitarian crisis if such weapons are deployed. And it also undermines regional and global security as it increases the number of actors capable of deploying nuclear weapons and potentially also destabilizing the delicate geopolitical balances that are already in place. And as a result, the IAEA safeguard system, which was established in 1959, has been a very vital component of the Non-Proliferation Treaty as it works to verify the compliance through monitoring and inspection of nuclear materials and facilities. And although the safeguard system started before the NPT came into force, the NPT negotiations led to the adaptations to meet new obligations, which have strengthened the safeguard system. And in the NPT, it is required that non-nuclear weapon states accept safeguards on all their nuclear materials in their territories, while the nuclear weapon states are expected to work towards disarmament. So that's just like an overview of what the NPT states about safeguards. And the International Atomic Energy Agency safeguards nuclear power plants through a set of technical measures to independently verify that states are honoring their international legal obligations to use nuclear materials for peaceful purposes. This involves implementation of comprehensive safeguards agreements, additional protocols, and others that grants the agency expanded rights of access to information and sites, which would include fuel fabrication sites, uranium mines, enrichment plants, and waste sites. So the agency collects and evaluates safeguards relevant information, develops approach, and these measures are very essential to deterring the spread of nuclear weapons and provide credible assurances that the states that have accepted the safeguards on all their nuclear materials in their territories are deterred from gaining access or spreading nuclear weapons and provide credible assurances that these states are abiding by their legal obligations related to nuclear materials and activities. Now, for the proliferation risks that are associated with SMRs, making it very important for safeguards to be strengthened for their technologies is basically based on the fact that they have a dual-use nature. I mean, when I talk about the dual-use nature, I'm practically talking about the fact that they can be utilized for both peaceful purposes and weapon development. SMRs are attractive to proliferators due to their lower cost, as I mentioned earlier on, compared to the larger power reactors. Because of their modularity and other characteristics that they come with, they tend to have a lower cost of acquisition compared to the traditional larger power reactors that we know. And the power reactors can produce, and these power reactors are capable of producing significant amounts of weapon-grade plutonium on shorter cycles. Also, SMRs have had their historic roots in military applications, specifically in the development of naval reactors for submarines and naval vessels. And as this is so, it is also important to know and understand and keep in mind that they've also been used for research and development laboratory projects. And it is also important to know that the experience that is gained from these military programs laid the foundation for the advancement of civilian SMRs. And today, many SMR designs draw their knowledge and advancements achieved through the nuclear programs from the military history, incorporating features like compact reactor cores, passive safety system, and the modular designs. And while the military pursuit of small, portable, and reliable nuclear power systems influence the concept of SMRs, their focus have been shifted towards addressing energy needs and promoting sustainable energy sources for civilian use. That is, they have evolved beyond their military origins and are now primarily aimed at meeting civilian energy demands, such as reducing greenhouse gas emissions and ensuring secure and sustainable energy generation. But then even so, there are still some concerns about the possibility of clandestine construction and diversion of SMRs for military purposes. A further explanation of the reason why there are proliferation concerns with SMRs is because the deployment of a lot of SMRs across different countries could strain the capacity of regulatory bodies and international organizations effectively monitoring and verifying their compliance with non-proliferation commitments. And also the buildup of transuranics in nuclear reactors, and then the characteristics of plutonium vectors in some reactors are also important points for consideration when it comes to proliferation risks associated with SMRs. I will talk more about these later in the slides. So the next point also talks about the fact that different SMR designs would have different resistance to proliferation. As it is known, there are several SMR design types under development and research. And finally, geopolitically, SMR development kind of intersects with the current innovation and an arms races that is ongoing between great powers around the globe. And so this means that it kind of presents both opportunities and challenges. So this is a vital point to explain the reason why the proliferation risk is being considered. Now I'll move on to talk about the challenges. I'll start with the design. By the basic points that are being considered when it comes to the design of currently exposed SMRs is, first of all, unload refueled reactors. For such reactors, safeguards considerations here would be in the direction that there is the increased frequency in spent fuel handling compared to offload refueled reactors. And this means that unload refueled reactors pose challenges for nuclear safeguards because the continuous refueling process would make it more difficult to monitor and verify the nuclear material in real time. The traditional safeguards are designed around periodic fueling cycles, but not with unload refueling. And this is going to mean that there will be a constant influx of fresh fuel, complicating efforts to accurately account for and track nuclear materials. Now, when we talk about the breeders, examples like fast neutron SMR designs are able to convert abundant uranium fuel to plutonium, which poses a unique challenge for safeguards due to their ability to produce more fissile material than they can consume. And so it makes it very important that such technologies are closely monitored and controlled in the process to prevent the proliferation of nuclear weapons. And then advanced fuel cycles. When I talk about advanced fuel cycle, I'm trying to explain the fact that advanced reactors could be non-light water reactors and use non-standard fuel cycles that could be unfamiliar to safeguards inspectors. And so they would require time to develop an effective safeguards approach, which would require that safeguards experts work with design teams to tackle this issue. And fuel element size, smaller reactors means that there will be smaller cores and shorter fuel elements. And then this means that the small size will facilitate item concealment for those planning on diverting their use. And this will be an incentive for international safeguards regime to develop monitoring methods specifically for SMRs. Now, the low thermal signature could also be explained in the fact that SMRs would have low thermal footprints, and that is they'll be kind of harder to use satellites or other forms of remote sensing to verify their operations, which would pose an issue for safeguarding such technologies. And then when it comes to enrichment, although almost every reactor is designed in such a way that the enrichment of the fuel doesn't really pose an issue. Some designs are known to use over 20% enrichment of fission products mixed with fissile materials that are highly radioactive. And so this will require special handling. And then highly enriched uranium would also mean potential for more nukes or non-state theft, and which would increase the cost of safeguards and then the need for safeguards for such technologies. And on excess reactivity, SMRs with the excess reactivity factor explains the fact that a low refueling frequency means that the core design would need to have high excess reactivity and burnable absorbers. Now, the excess reactivity in SMRs can pose challenges to safeguards because it may indicate the potential for the reactor to operate at power levels beyond what is declared or agreed on. And since safeguards rely on accurate declarations of reactor characteristics, including power levels and fuel composition, if there is excess reactivity that goes undisclosed or unmonitored, it raises concern about the possibility of unauthorized or unintended use, which potentially leads to proliferation risks. And so then there is a need for ensuring accurate and transparent reporting of reactor parameters, which would be crucial to enable effective safeguards. Now, for the coolant opacity, for the SMRs that use non-transparent coolants such as molten sodium or lead bismuth, the optical viewing of fuel in the core or in spent fuel storage is a little bit hindered or is hindered in a whole, and this could pose an issue for safeguards. And when we talk about the spent fuel storage geometry, because the fuel elements are smaller, they would need to be stored vertically for cooling. And there is also a strong economic incentive to stack fuel to reduce the storage footprint, which is a good thing, but then this would also lead to lack of direct line visibility of the fuel element from above during safeguards inspection or nuclear materials tracking. And this would pose a challenge to safeguards inspection. Moving on, generally, aside the designs, the challenges that could arise with SMRs would be nuclear verification, which could stem from any of the points that I've already talked about, that there could be challenges associated with performing nuclear verification with SMR facilities. And then there could be challenges with the implementation of safeguards when it comes to SMRs, because there could be the possibility that the IAEA may lack direct communication channels with the facility designs. And so the designing of a safeguard safeguards approach specific to SMRs could be a little bit staggered. And for non-proliferation and IAEA safeguards, there would be the need for development of there will be the development of factors that SMRs will pose challenges for, and then at the same time opportunities for traditional concepts of non-proliferation and safeguards. The concepts that have been in place for decades now, that have been used for safeguards in all nuclear facilities, would face challenges when it comes to SMRs, because those technologies are quite advanced, and so there would be the need for advancements in these concepts for non-proliferation and then safeguards. The next would be on safeguards by design. This is going to be touched more on by Dr. Jeremy, because it basically talks about how the IAEA is preparing to safeguard SMRs. And so I'm going to leave it to him and move on to my last slide. For potential synergies, first of all, synergies refer to the interaction or cooperation of elements, components, or processes that result in a combined effect greater than the sum of their individual effects. And in the context of various systems and activities, synergies occur when the combination of different parts or aspects produces a result that is more efficient, effective, or beneficial than the outcomes that could be achieved by each part independently. And when it comes to, sorry, move fast. And when it comes to safeguards, safeguarding small modular reactors whilst exploring potential synergies, it's a very crucial topic that needs to be discussed, because the potential synergies between optimal design solution, the nuclear materials accountancy, control, and conflict is very important to safeguarding SMRs, because this would affect the integration of safety, physical security, and safeguards or material control, as well as accounting for material control and design in the early stages of the SMR designs. And so as I have broken it down into this table here, we can see that there are synergies for optimal design solutions, and then also for the accountancy of nuclear materials, and then control when it comes to SMR. But for each synergy, there are conflicts. But then in all, it's important to understand the fact that addressing conflicts between optimal design solution and the nuclear material accountancy and control would lead to a mutually reinforcing strategies. And this could be a very good starting point for safeguarding SMRs. And although conflicts may arise if the design introduces complexities that impede accurate material accountancy or compromise their ability to respond promptly to security concerns, a combination of all these factors incorporated in safeguards design would go a long way to protect SMR facilities from being diverted to weapon use. Basically, this is what my presentation is all about. And thank you very much for your attention.
Thank you very much, Adjoa. This was very interesting. Thank you for all your thoughtful analysis of both the opportunities that we will gain from the deployment of SMRs, but also the things we still need to ponder about, some of the challenges, and also highlighting the synergies and the importance to consider the 3S in all aspects, safeguard, safety, security. So thank you very much. And thank you also for being so brave for talking to all of us today. We really appreciate that. Next, I would like to hand over to Dr. Jeremy Whitlock from the IAEA, who will speak to us about what the IAEA does in developing safeguards approaches for all these new reactor types. So Jeremy, please go ahead. The floor is yours. Thank you.
Thank you. Okay, so Joe did a nice job there of setting up the story. There's very little more that I need to say, except perhaps to let you know what we're doing about everything she was saying here at the International Atomic Energy Agency. So I work in the team that actually has to worry about all that stuff that Joe was talking about, because we have to prepare to safeguard these interesting machines. We're not just interested in them, and we don't just encourage them to be built, and we do, but we have to also be ready to safeguard them. They have to be run safely, securely, and be safeguardable. So these kind of things, and when I say ready, I mean, and here's the thing: we have to actually be able to apply safeguards as soon as these various reactor types receive their fuel. And if it's a conventional reactor type, an LWR, a heavy water reactor, we already know how to do that. But if it's one of these things on the screen, we actually do not have safeguards approaches in place. So time is needed to develop them. So if you look at, I mean, we heard earlier that there's upwards of 100 different types of designs that are coming along. Some of them are what we call floating reactors, like the one that's operating in Russia as we speak. And there's several companies that are talking about this. Now, these are not propulsion nuclear reactor SMRs. They're SMRs that are on a barge, so they don't provide the energy to move the ship. It's not a ship, it's a barge, and it gets towed to a port. So we have a couple of interesting factors there. One is that you have the advanced SMR to begin with that we don't have a safeguards approach for, and we also have not safeguarded a reactor that's on a floating vessel before. And we will need to be ready to do that. And there's some other features of that too, because that vessel will bring that reactor probably already assembled on the barge from another country, and that other country will be most likely under a different type of, well, it will for sure be under a different safeguards agreement from the customer country, but it'll also be under most likely a different kind of safeguards agreement, because it's most likely going to be a nuclear weapons state and not under comprehensive safeguards. So that top left corner is an interesting one, and we're doing quite a bit here at the IAEA to prepare for those. And the one that's in the picture is the one that's operating in Russia. That's not under safeguards, but it's just there as an example. In the top middle, I have microreactor fleets, and this is a common proposed application of SMRs. These are very small, relatively small reactors in the tens of megawatt energy range, and you can have multiple versions of these, multiple modules of these, operating beside each other. And what's good about that size range in the 5 to 10 to 50 megawatt electrical range is that this is the size of diesel generator sets that are operating today in places like northern Canada at mining sites, military sites, and small remote communities. And there's no reason to be burning diesel fuel in these remote areas. We knew how to make nuclear energy 70 years ago, and we're just now getting around to building reactors small enough and economical enough and safe and secure enough to operate them there. They also have to be safeguarded though, and that's a challenge. In the top right, we have innovative fuel cycles. That's a broad category. So simply put, that picture there is the pebble bed fuel. That's for the high temperature reactor operating in China. So that's an actual operating facility, which is not under full safeguards either, because it's China and it's a nuclear weapons country, so not under comprehensive safeguards. But we do apply some safeguards at that facility. When China, for example, wants to sell a commercial version of that reactor, which uses hundreds of thousands of those little fuel spheres, we need to be able to track every single one of those through the process, and they look just like that. There's no ID number on them, and they will go into a container. They will not go into a spent fuel bay looking like that. They will go into a container, and the container you can't see through. So we need a way to verify hundreds of thousands of those little spheres independently. The bottom left is transportable sealed cores. Well, so the floating reactor example is also a transportable sealed core, but here is the type that comes across a border from another country and it's on a truck. Small reactors that will be fueled at a factory and then sent over. So similar situation to the floating reactors in that we will need to do verification of the construction and loading of the fuel in a different country. And then the fuel will come and the reactor will come and in some cases will operate for 10 or 20 years. And it's a long time to not see the core of a nuclear reactor. The operator may never see the core of their own nuclear reactor. The operator may never even, the operator may be from a different country too, which is another issue. So we deal with that. The bottom center, remote locations. Well, I mentioned the microreactor fleets. That's this picture on the bottom here. This is actually of interest. Maybe this is the most northerly continuously occupied location on the planet. The most northerly continuously operated and probably the coldest continuously occupied location. It's a military base in the north of Canada called Alert. And it's currently heating itself with diesel generators, and it's thinking they are thinking of putting small reactors there. And so here the issue is that location. Imagine having to independently inspect the reactors operating there. So there is no sort of unannounced visiting of these sites. Nobody goes to this location on the planet unannounced and randomly. It's well planned in advance. And so we need to be doing things differently than sending human beings up to places like that. So this speaks to the need for advanced technology for remote monitoring. And then finally, in the bottom right, new industrial applications. Here we have a oil and gas rig, an oil or gas rig. I don't know which one this is, but we have been approached by industry that extracts fossil fuels offshore of various countries. And many of these countries that have the oil reserves, like for example, Ghana, do not have an extensive nuclear industry. And if a private company comes along and builds one of these things in their territorial waters, and then wants to put gigawatts of nuclear power onto this thing to reduce their carbon footprint, well, they're also extracting fossil fuels, so that's kind of ironic, but they want to decrease their carbon footprint, and you were then adding to the nuclear infrastructure of the country in whose territorial waters you're operating. It doesn't matter who owns the oil and gas rig, it's where the facility is located. So there are issues there, including how one would do inspections on a facility like that. So this is real world, every one of these things on the screen, real world issues that have come to the IAEA. Thankfully well in advance, and that's really the story that we're talking about today. So Adjoa talked about safeguards and the need for them. I thought I would just give an example of what do we actually do when we go in field, when we go to reactors. So you see various pictures here of people leaning over railings with cameras, looking down into spent fuel bays. So that thing in the upper right actually is called the Cherenkov viewing device. And if you've heard of Cherenkov radiation, this is the blue glow that comes off of spent fuel when you see it. Also reactors. If you look into a research reactor water pool, you'll see a blue glow, and also the spent fuel bay. The blue glow is the radiation from the spent fuel, and we can use that at the IAEA, or inspectors can use that, looking through a device. It's mostly in the ultraviolet range. So if you look at it with a device that filters the UV or passes the UV and filters the rest out, you can get a good look at the spent fuel, and you can tell which ones are really spent fuel because they're radioactive, and ones that look like spent fuel but they're actually dummy fuel elements that have been placed there, which means the real spent fuel has disappeared. And Adjoa talked about plutonium. That's what we're looking for in the spent fuel. Any uranium that sits in a nuclear reactor for any length of time creates plutonium. Plutonium is also a fuel, but it can be used also like uranium in nuclear weapons. And so we need to know where all the plutonium is. It's in the spent fuel. That's why we're interested in spent fuel, even though it's been depleted in uranium and it's very radioactive. It also contains a lot of plutonium. And so the accountancy that I'd speak about in this first bullet, that's the nuclear material accountancy of the facilities themselves. That's the same nuclear material accountancy and control that you would do for security purposes, for safe operation. The operator needs to know where the nuclear material is. And one additional reason for knowing where it is because the operator needs to report this information to the IAEA through their government. And so this is what Safeguards is the nuclear material accountancy of a facility, basically the database of how much nuclear fuel, uranium and plutonium and thorium, if that applies, is at each facility, and where it is at each facility. And then inspectors will show up, like you see in the pictures here, and verify that. So then in between inspections, we need to know that the material has not actually moved, and so we apply seals. And for example, the bottom right, you see an inspector applying a thing that's on top of that container is a seal, which is an agency device, tamper indicating device for letting us know in between inspections that that container has not been opened by the operator. Because in safeguards, the operator is the design basis threat. That's what makes safeguards fundamentally different from security, where security worries about external threats or internal compromised employees, so an internal threat or cybersecurity. For safeguards, what makes it fundamentally different is that the operator themselves and their government and their police and their army and their intelligence services are all part of a theoretical, hypothetical plan to develop nuclear weapons. And so you have to put your own equipment in the field, and you have to put your own seals on containers. And only inspectors can access this equipment and those seals. And same with these cameras that you see in the bottom here, the blue agency cameras looking at the top of a reactor in that picture. Or we have our own detectors. You see, looking at those yellow storage sites with an agency detector, which tells that the inspector not just the radiation levels, but also something about the type of nuclides that are in the containers. And then the first two bullets here wouldn't really matter if the place wasn't really built the way it was supposed to be. So we have to verify the design. And that's simply inspectors, perhaps like in the bottom left picture, walking around a facility and with blueprints, checking that it's been built with the way it's supposed to, checking that it is being built. So we want to be there before the fuel is put in. This was the issue with the floating reactors and the transportable reactors, if you recall, that we need to see the thing being built, which means in those cases going to a different country. Normally, you just go to the site and you see the hole in the ground, and then the hole in the ground is filled with a reactor building, and then the reactor, and then you see the fuel go in the reactor, and then you follow the life of the reactor, and you're always inspecting the facility, and you're looking for doors where there weren't doors before, or containers where there weren't containers before, or there weren't supposed to be containers, or things like that. And you have cameras as well that are keeping track of all this. So those three bullets are what we do in the field during visits and inspections. And then we can also, in most countries under safeguards, do environmental sampling at many sites, which simply is looking for things that have not been declared, but they're doing anyway in a covert manner. So if you were to be irradiating uranium secretly in your power reactor and making plutonium and moving that plutonium to a separate reprocessing place, and we suspect where that reprocessing place is, we might go there, and even though it's not a nuclear facility, and we might take a filter paper and swipe the surface of shelving or desks, and look for particles of plutonium. And we do that by sending the filter paper back to Vienna, or just south of Vienna actually, to our laboratory, and they run it through a mass spectrometer and look for these nuclides. So this is what safeguards looks like, and this is what we do all the time now in traditional reactors. And the thing is, we have to do this as well with SMRs, and regardless of how advanced the reactors are, this is what our mandate requires us to do. So a bit of background here. This is a bit of a busy slide that just tells you what we did in 2022, which is the last year that they compiled this information. There'll be another one coming out for 2023 soon, I guess. So it basically is, it safeguards by the numbers. And I just want to highlight a few things that are of interest. Number one, 189 states are under safeguards, and that is most of the countries on the planet. So that's a good thing. Secondly, this number here, 231,000 almost significant quantities of nuclear material under safeguards. So what's a significant quantity? You can think of it as a critical mass. So the mass that you need to make a nuclear weapon. It's close to that. And so here you have 250,000 of weapons in theory that are not in being made because they're under safeguards. Is one simplistic way of looking at it. Is that all the nuclear material on the planet? No, there's about that much, again, significant quantities in the nuclear weapon state. So this represents only the amount, about half the nuclear material that's on the planet, and the other half is in nuclear weapon states and not under comprehensive safeguards. So there's 5 nuclear weapon states according to the NPT, the Non-Proliferation Treaty, and the rest of those 189 states are most of them are non-nuclear weapon states. And so another interesting item here is that almost 3,000 in-field verifications. So those things that I listed on the previous slide, 3,000 trips by approximately 10% of that is about 280 inspectors that are designated to go to countries. So you can do the math, and that's how many times they're going out. A lot of trips. And what are they doing? Well, they're doing all the things I listed, but one of them is applying and checking seals, and there's 25,600 of those. So that's just an impressive number. It's sealing not just containers of nuclear material, but also doors and cabinets that have IAEA equipment. And this is an interesting number here, remotely monitored facilities. So 159 nuclear facilities are remotely monitored. That means we don't have to go there to get our information because it's being sent, it's being detected by cameras or radiation detectors, and the information is being sent to Vienna remotely. That is how we need to be doing safeguards in the future across the board, especially for SMRs and especially for complex advanced SMRs for the reasons that I'll get to. And so you can compare this number 159 to the number just to the left of it here, 1,353 nuclear facilities under safeguard. So approximately 10% of the nuclear facilities are being remotely monitored. It's a relatively small number. One reason that remote monitoring is good is because this works even during a global pandemic like we recently went through. And so any device, hang on, so phone was just ringing, any facility that was being remotely monitored continued to have what we call continuity of knowledge through the early months of the COVID pandemic in March, April, and May of 2020. Every other place lost continuity of knowledge because there was no information coming, and we don't know what's going there, and we couldn't fly there or even cross the border to go into the country. And so we had to regain continuity of knowledge at hundreds and hundreds of facilities as soon as we could in 2020. And that continued obviously for the next couple of years as well during the pandemic. But for the first 3 months, it was an issue across the board. And for the places that had cameras and detectors sending information to Vienna, there was no issue. So that is how we should be doing safeguards in the future. So then the challenge with advanced reactors is, as I mentioned, they have to be safeguarded when deployed. So we don't stand in the way of progress. We're the IAEA. We encourage new systems, and they need to be safe and secure. But one thing they also need to be is safeguardable. Regardless of how tiny they are, they still need to be safeguarded, even if they're a little 10 megawatt reactor. Regardless of how complex, regardless of whether we've seen anything like it before, we need to safeguard it, regardless of how difficult it is to get to the facility, or even if once you get physically to the facility, can you get around the facility to do verification of the design? Or even this, can you get to the spent fuel bay? Lots of SMRs are being designed with small footprints and robotic machinery, and they're not really thinking that human beings need to access on a regular basis some parts of the facility. And they're quite surprised to learn that that's actually something they're responsible for by virtue of living in a country or selling to a country that is under comprehensive safeguards. And also, regardless, I mentioned this or alluded to this earlier with the floating reactors, regardless of who the owner and operator is of the technology, it can come under a flag of another country. It can be operated by people from that other country. It does not matter. It matters where the reactor is being operated, and their safeguards agreement. So that all would be fine if vendors generally knew what I've been telling you, and that's not the case. However, many vendors are not aware of this significant customer requirement. They're aware of a long list of customer requirements, even the security requirements, which are the domestic needs for the country they're selling to or the country they're in if it's a domestic build, but they're not aware of safeguards. And that could be because they're simply not aware of international safeguards. For example, a lot of design companies are in nuclear weapon states, which as I was saying, are not under comprehensive safeguards. So it's not part of the design community's culture to be aware of international safeguards. So in the United States, for example, there are many vendors selling SMRs. There is a lot of expertise in the United States in international safeguards, but it exists at the policy level, at the government level, and in the national labs, but not necessarily the vendors. And as I mentioned, some of them are quite surprised to learn about this important customer requirement. Sometimes they know about safeguards, they've heard about it, but they think it's just traditional safeguards. So they think it's an inspector shows up, does some walk around. They might have a case with a camera in it, and they install a blue camera, and that's the end of it. That's just the beginning of it, actually. And as for complex designs, we may need complex safeguards, or advanced reactors may require advanced safeguards. And I would even take that may out of that sentence and say advanced reactors will require advanced safeguards. And here's the crux: this requires R&D to develop, because it may require a bespoke or customized instrument, a device, a radiation detector, which gets integrated with the operation of the reactor itself in a safe and secure manner. So we don't want it to trip the reactor or to compromise the security systems, but it needs to maybe send information in a cyber secure way to Vienna, as I was mentioning. That requires R&D, and the R&D is not done by the IAEA, and it's not paid for by the IAEA. And that really surprises a lot of vendors, because that R&D will likely be done by the member state itself and probably the vendor, because they are the expert on their technology, and where the funding for this comes from is another issue. And the time for this, if it's sufficiently innovative safeguards technology, is roughly 10 years from thinking up the idea to operation in the field where you can draw safeguards conclusions in a confident manner. About 10 years, because it also has to go not just through the R&D stage of the developer, but it has to come to the IAA, and then we have to authenticate it and validate it for use in the field. So it's a long process. Fortunately, that's where we are in SMR development. So that's why I bring it up when I'm speaking to SMR designers. And then finally, in case anyone is confused about security and safeguards, because we've often heard, and proliferation resistance, because we often hear that advanced reactors, one of the pillars of new reactors is to be more secure and more proliferation resistant than traditional reactors, and that's absolutely true. But there's a misunderstanding that proliferation resistance equals safeguards, and it does not. Proliferation resistance is the extent to which it's difficult to proliferate. So fuel that is compact, or that example I gave where a core operates for 20 years and nobody sees it, that's very secure, potentially, from outside attackers anyway. And it's possibly a lot of safety advantages as well. But if you are the owner of that core, if you're the one in charge, and theoretically you're the one involved in a proliferant scheme, you have all the access in the world for 20 years, and the IAEA does not, because there's no refueling, and so it does not even know what's going on in the core. And so we need to know. So there you have it, inherently proliferation resistant, perhaps, because then even the operator that has the thing will have difficulty getting at it while keeping it running, so to speak. So it's inherently proliferation resistant, but we can't verify it. If you can't verify it, it's not really very safeguardable. And safeguardability is a component of proliferation resistance. It's an external component of proliferation resistance. So you need to be not just inherently proliferation resistant, but externally proliferation resistant as well, which means that the expectation for safeguards is reasonable, and that's not going to break the bank. And there's actually a technique that we can do. And so that's something that needs to be taken into account as well. So then when we apply safeguards for SMRs, what kind of things are we going to be doing? Well, the first bullet I've talked about, these unintended monitoring systems. That's our phrase for Geiger counters, cameras that are operating at the facility. An inspector does not need to bring them in a Pelican case when they do their inspection, but it's been installed when the facility was constructed, and it's running on its own with its own power supply, and the data goes to a secure storage location, and it can hopefully store up to 3 months or more of data, or longer, and even better, it sends the data remotely to Vienna. So unintended monitoring systems and remote data transmission. It sounds kind of trivial for a lot of things today. All of our cars, if you buy a recently made car, it's probably remotely talking to the factory all the time. This is something we accept, but just in the world of safeguards, as you saw from the numbers I put up, it's not widely used, and we're bringing it in as fast as we can, and we will have to do this more and more with advanced systems. That requires, however, talking to the vendor up front. This also requires digital connectivity because these systems talk to Vienna through secure internet, so you need internet. That picture I showed you of the north of Canada, there is no internet up there. And even if there were, it's not going to be reliable and high bandwidth either. So we need to have that in those areas if we want to not have to go there in person. Also, if you're going to have remote security or remotely operating, you hear about remote operation as well. So all three S's, safety, security, and safeguards, might need this one synergy here to talk about synergies as Joe was introducing. So safeguard seals, we will need to go and apply a seal in another country, perhaps that's fueling a reactor and sending it across the border. It might be a seal that we already have, or maybe it's a new seal. Maybe it's a seal that has to operate for 7 to 10 years next to a reactor core that runs for that long before it's fueled. Who knows? But we need to look into that at least and address those questions. And also, so design verification, particularly under these transnational, as I call them, supply arrangements. Also design verification for small footprint facilities as well. Continuing with what will be new about safeguarding SMRs, well, this first bullet is just a catch-all, new safeguards approaches. So that basically means what are the procedures for safeguarding these technologies, and we need to develop them, including potentially customized agency equipment or joint use instrumentation. Like for example, possibly we can share data from an operator's instrument if we can authenticate the data and make sure that it's not been faked. Possibly thermal power monitors, which on microreactors, so we measure the heat flow, the temperature and flow and pressures for large research reactors, not for power reactors so much. We will need to do that for some SMRs going forward, and possibly process monitoring, which is to take all sorts of data from the running of a say a molten salt reactor, which is almost like a chemical facility, chemical processing facility from a safeguarding point of view, like a reprocessing facility. We need to take data from many points and follow the process, which requires possibly sharing of data as well. There are some statewide issues here. There's nothing to do with the designer, but maybe the country where it's going to be built. For example, I mentioned high bandwidth internet. That's an infrastructure issue that helps safeguards and also security and also possibly safety. So it's good to have internet for safety and wherever you're going. And they don't want to be running these having lots of staff at these facilities, and we don't want to be sending staff to safeguard these facilities on a frequent basis. All of this requires training, not just for safeguards authorities in emerging nuclear energy states, which is the example on the screen here, and that's very true that we need that, but also for the IAEA, because we need training on what's inside those nice pictures of reactors that I was showing you, which all come from the internet, and we need to talk to the vendors and see their blueprints way before they start to build these things. Now, the good news is that even though all of what I've just talked about requires time, I mentioned 10 years possible R&D for new instrumentation. Time is what Safeguards by Design provides, and that's what my area is promoting. So Safeguards by Design, why is it by design? Well, because safeguards typically doesn't happen during the design period. It happens during operations. So everything else is included during the design stage, your national safety and security requirements and other standards and codes, certainly your operational goals. These are the customer requirements that designers are familiar with. And then the safeguards is this thing that's an operational issue, and that's legally where it is. And so that's part of the problem, is that you legally have to declare your nuclear material accountancy, start doing that, and your design to the IAEA when there's a decision to construct. And they start providing information, design information, and then accountancy starts when the nuclear material arrives, and that's way down the road towards on the design stage. You've already got a design that's ready to be built at that point. That is far too late for advanced reactors for the reasons that I was talking about. So Safeguards by Design is not moving that big yellow rectangle on the right. The international safeguards obligation starts there, we leave it there. But the conversation starts back when the other things are being talked about. And you're talking about safeguards and safety and security all together, and the synergies and possible conflicts, as Joe was talking about, and that's the 3S approach, the 3S's. So it's integration of safeguards into the design process. It's voluntary because we leave that yellow box on the right where it is, and we hope that vendors learn about the benefits of this and then come talk to us. And it's also a life cycle and fuel cycle tool, meaning that it's not just new build, but it's whenever you're doing any design decision. So even deciding how to decommission the plant, there are safeguards issues to do with decommissioning, even though that's way down the road from the SMR designers or the operator's point of view. Where is the waste going to go? Are you going to build a dry storage facility to move the fuel out of your spent fuel bay? There are serious safeguards issues with dry storage containers, and so safeguards by design is really being smart about those choices when they come along. So this concept is not actually new. It's not widely used because the world is full of light water reactors and heavy water reactors, for which we have developed safeguards approaches a long time ago. But originally, when heavy water reactors, looking at the right side of the screen here, when they were first developed, there was no safeguards approach for them, and they needed to be safeguarded in a very different way as well, because they are refueled online, just like many small modular reactors are that are proposed today. So a lot of those things I was talking about, the unattended monitoring systems and remote data transmission, were developed by the vendor for those reactors. And that's the same kind of concept we're going to be using for reactors going forward. And also the dry storage containers, because CANDU fuel pushes the uranium fuel through about 5 times faster than a light water reactor. So you fill up your bay a lot quicker. And so right at the beginning of the industry, they started moving fuel to dry storage. So decades ahead of the rest of the world in terms of building dry storage containers. And those dry storage containers you see in those pictures have safeguards included in them. There's no seals on the outside of these containers. They're all embedded in the concrete through conduits that have been put there in the design. Similarly, on the left, you've got another interesting part of the fuel cycle, which is a reprocessing plant. And this one is in Japan. So it's actually in a country under comprehensive safeguards, and it's the largest reprocessing facility under safeguards in a country under comprehensive safeguards. And the safeguarding of that was only possible by extensive involvement of the designer and the operator and the state itself, which funded a lot of the development. So there's that funding issue, which catches a lot of people's attention. Which brings us to the benefits. So there's reduction of burden for both the operator and the IA. That's the big part. That's the big message, because a lot of people think, well, if we make a tweak to the design that helps the safeguards, aren't we just helping the IAEA? How does that help the operator? If the IAEA has to come a lot with an inspector and take samples and stop operations while it takes samples and interrupts operations, that's a burden to the operator. And so you could actually reduce inspections through safeguards by design. And there's a good example of that in the UAE right now, where the United Arab Emirates just recently started their 4th light water reactor, and the inspections at those reactors are a fraction of the inspections we do at light water reactors that have been running for decades, because the UAE started right from the beginning and said, we would like to reduce the number of inspections. How do we do that? And we said, well, through unintended monitoring systems and remote data transmission, and then we will randomly show up when we feel like it to verify that everything's working. And that's the approach we're proceeding today. We need to do, as I mentioned, that all the time going forward as much as we can. You enhance the possibility then of using the technology I was just talking about by talking about their needs sooner. You reduce the need for retrofitting, because if you don't talk about it before, you will have to install safeguards anyway, and you will do it very quickly because you don't want to interrupt the operations, and it won't be as good as doing it ahead of time, and it'll also be a lot more expensive. Anytime you retrofit anything into an already built nuclear facility, like putting a penetration through an already poured concrete seismically qualified wall of containment, it costs a lot more than if you design that penetration from the beginning. As I mentioned before, you facilitate the shared use of operator equipment and process information. which will be a benefit, and you increase flexibility for future safeguards equipment installation, because guaranteed safeguards will change over the 60 or 80 years that these reactors are running. I mentioned about the synergies and the conflicts. So you avoid the conflicts and you leverage the synergies with safety and security. You facilitate terminating safeguards on rad waste, which I didn't talk about, but that's at the other end of operations. You're going to generate rad waste. It can be, you're not going to terminate safeguards on spent fuel, but you might be generating rad waste as part of your, say, pyroprocessing technique for reprocessing your waste and putting fuel back into your reactor that generates rad waste, which nobody wants to apply safeguards to. We don't, and the operator doesn't want us to, but we will if we have to. And so there's a way to terminate safeguards if the concentrations of the nuclear material is low enough. And so that requires discussions up front. So overall, as I hope I've communicated, this reduces the risk to the scope and the schedule and the budget of your build plan, the budget, because you just might have to help fund the development of new equipment. And it encourages a better understanding of the customer's needs. If you're designing, and even though you're not in a country, say, that has comprehensive safeguards, you know your customer does, and that's actually a big customer requirement. And the IAA also has a better understanding of what's going on. So everybody understands what's going on, and that is just good design engineering, to have good communication. That's all this really is. So it benefits all stakeholders, not just the IAEA. And I just want to quickly throw this up. We are doing everything I've talked about. Okay, so that's the reason for doing safeguards by design. What are we doing? We are talking to various vendors at these countries. You see, not at the countries, they're actually coming to Vienna. Vendors from these countries are coming and talking about their integral PWRs or BWRs, or their molten salt reactors, or their pebble bed reactors, like the ones I showed in that picture. We are talking to China about their commercial version of that reactor. Floating reactors. We collaborate internally at the IAEA. There's a vast storehouse of knowledge here at the IAEA in the other departments other than safeguards. There's a lot of knowledge in the Department of Safeguards too, but there's a lot of expertise in these new technologies in the Department of Nuclear Energy and Nuclear Safety and Security, for example. And so we do interact with them in a structured manner, in a framework that allows us to coordinate our activities and also attend their research projects or their technical meetings and have input, and vice versa, which is that's safeguards by design, or that's 3S happening at the IAEA. And we of course engage externally to raise awareness of everything I've just talked about. And if I was talking to a bunch of vendors, then I would then say, here's how you contact me, and we would start the discussion. Or I would say, hey, here's some information. We don't have a standard that you could follow like you would in safety or security, because safeguards is more of a game theory activity where you need to just raise awareness of what the expectations are. There's a whole area I can get into there, but the point is we do have guidance, and it's available online. For example, the two series of documents I have on the screen here are available to help designers get up to speed on what we mean by safeguards. And that is the end of my slides. Thank you very much.
Thank you very much, Jeremy, for giving us these insights about what the IAEA does in developing safeguards approaches for small modular reactors. And as a former IAEA safeguards inspector, and also, what was my title? Safeguards analyst working in your division, I'm fully aware of all the challenges that lie ahead of you, in particular of the announcement of trying to triple nuclear energy by 2050 with the deployment of many new reactors. So I am wondering, has the IAEA done a calculation of the costs that will be associated in supporting this tripling of nuclear energy, just from the safeguards point of view? So you will need many more inspectors, you will need training for the inspectors, you will need all these new technologies that are under development and still will need to be developed, and the infrastructure that will be needed, and where the money will come from.
Yeah, most importantly. Yeah, so the short answer is no, I'm not aware of a strategic calculation of what that would look like. And I think it would be difficult at this point because frankly, it's hard to get a handle on it. So what we can do is look at the different technologies and say, well, that one's going to be a challenge, like molten salt reactors for sure. We can put a circle around that. Pebble bed reactors for sure. We don't know how many molten salt reactors. The best we can do now is to go on to the vendors' websites and see, well, they've got an MOU signed with this country or with that country or that regulator. Some SMR companies are a little further along. Some are already constructing, and some are about to construct. Those ones that are further along at that stage tend to be the ones based on light water fuel anyway, and so they don't have those major challenges that I was talking about. They have still some challenges. And for example, if there's multiple modules of light water fuel based integral PWRs, if you have multiple modules at one site, now you've got a resource issue, because now you've got maybe it's not just one SMR, it's actually 6 or 12 if you're looking at the new scale design in one spot. And if we did safeguards the traditional way at an LWR, we'd be going to this one site 4-6 times a year. And so we need to do it that differently. And they only have one fueling crane that refuels packages of fuel, puts them in the spent fuel bay. And for example, the operator knows which fuel they just took, but the IAA doesn't know. And so we need to know which fuel came from where. The best idea is maybe to just have data coming so we know where the fueling system is at all points, which is how CANDU reactors work. And that's why I keep drawing a line to the CANDU reactors and saying, even though you are an LWR designer and your system is an LWR and it's refueled, it's batch refueled, you actually have a lot of CANDU type, like you're actually sort of online fueled in a way, in a much lower frequency, but there's a lot of similar issues. So those ones that are coming soon, we're tackling those first, but they're also perhaps not the biggest challenges. The ones that are coming in the future, we know which ones are the biggest rocks in the stream that we're going to have to navigate around. But no, to your question, I don't think there's a strategic that I know of anyway, prediction of, okay, let's look at how many. I've seen kind of informal spreadsheets where, okay, it looks like this and this, and within 10 years there's this many, and 10 years is that many. But in terms of connecting that to resources and number of inspectors and importantly, new instrumentation that has to be developed by SGTS Technical Services, working in conjunction with the member states. I think we're early days on that. So hence my message.
Yes, good luck for that. I also have a question regarding some of the SMR types like breeder or burner reactors, which would require some of which would require reprocessing capabilities in the states that will be using them. So I think those types, I'm wondering whether those types of SMRs will be mostly restricted to nuclear weapon states that already have those capabilities, or whether non-nuclear weapon states would really build up all those additional facilities that would be required to run such reactors. And also from the proliferation risk point of view, what do you think about that option?
It's a very good point. Joe was mentioning one of the fundamental issues with inspecting at a fast breeder reactor is that you can't see the fuel through the molten sodium. So you can't use that device I was showing in the picture with the Cherenkov viewing device. It's going to have to be some instrument that you lower down that can see the radiation coming off. So that's the simple inspections for trying to detect diversion of the fuel, but then you're bringing up this issue of associated fuel cycle facilities as well. There's going to be reprocessing, and not just fast reactors, but a lot of the molten reactors. Their reprocessing is part and parcel of their design. Maybe not the first build, but that is part of the design. And so these will not be restricted to nuclear weapon states. At least I've seen no movement to do that yet. In fact, there's a molten salt reactor that is being planned in the near future in Canada, which is a country under safeguards, and they will be building a pyroprocessing front end to extract fuel from spent CANDU fuel. And so there's a few things in there where you're now going into a dry storage facility that's under safeguards and extracting fuel, and you're reprocessing it with a technique that we don't have a safeguards approach for yet. We've been working on it for a number of years, which is pyroprocessing. So it's a non-aqueous form of reprocessing, And then at the end of that, you're putting it into a molten salt reactor, which we don't have a safeguards approach for. And then the cycle, and then you're reprocessing again. So the whole thing is I would say, an interesting safeguards challenge. And the most interesting part for that particular case is probably the pyroprocessing, not necessarily the molten salt reactor, which in itself will present some interesting things too. So yes, lots of interesting work ahead.
Yes, indeed. Jeremy and Adja, we have one question here. How do you see the role of safeguards at the site licensing phase without considering the reactor redesign readiness? So at the licensing stage of the site.
Yeah, well, I can take a kick at that, Joe, if you'd like. The one thing that we encourage is that pre-licensing is a best practice that I think will be critical. So I would even put quotes around best and say it's almost critical practice going forward, that regulators should start before the legal licensing, site licensing process, encouraging all of this good discussion that Joe and I have been talking about, that you need to have intelligent customers, intelligent licensees that know what's coming along, and then they can start that ahead of time. And then the licensing itself, by the way, that pre-licensing process is the time when you would be doing safeguards by design. So a best practice that we see in the UK and in Canada, for example, that two countries that have pre-licensing regimes. So this is like safeguards by design. It's voluntary. It's ahead of the legal requirement for licensing. Part of that is to assess the safeguardability, and then the safeguards authority, which is also the regulator, selects vendors and puts them forward through our member state support program, which is on that one of the last slides that I showed, that where we're interacting with some of the vendors. So that's actually connected to the pre-licensing process, and that is best practice that we encourage.
Thank you.
I hope I answered the question.
Thank you. Does anybody else from the audience have any questions? You can just raise your hand or put it in the Q&A. I think this question has been answered. If not, I would like to ask Adjoa a question. So Adjoa, how come you got interested in SMRs? And can you tell us a little bit more about the status of plans for deploying SMRs in Ghana? Are there any plans like that?
First of all, I got interested in SMRs because I was introduced to it in a summer school that I attended. I got to know that there are other reactors aside the conventional large reactors that we are already accustomed to. I learned more about their design, the types, and then the ones that have come out, and the research and development. And then I developed the interest in it. I wanted to know more about it, what goes into their design when it comes to safety and security and safeguards, what is being done and all that. And I did a short research on that during that summer school. And ever since then, I've been reading about it, following trends and all that. And since it has gained momentum over the past years, it has become a strong area of interest for me as a woman in nuclear. And for Ghana, currently, I think, as I know, that they are still at the preparatory phase. I'm considering the milestone approach that is given by the IEA for any country that is interested in deploying a nuclear power program. I don't know if this is allowed to be said, but I kind of got the opportunity to attend one of the meetings officials from Ghana participated in their process of deploying their power program. And I can say that it's still in the preparatory phase, but I can't pinpoint exactly where it is, whether they've crossed milestone 1 or milestone 2 or wherever it is. But I think that they are making strides, and soon the power program would become a reality. That's what I can say about it.
Thank you, Ajwa. I wish Ghana a lot of success in that. I think Ghana is the leading African country after South Africa, of course, at least
Yes.
the leading newcomer country, I would say. So I wish your country a lot of success, and I also hope that you will find a role with your experience that you have acquired now to contribute towards your country's program.
Thank you.
I'm wondering, is there anybody else who has any questions from the audience? Don't be shy. We have all this an interesting topic here now with a lot of different aspects, and it's a unique opportunity. So, to come back to Jeremy, I think to my mind, the major challenge will be, in addition to what you have already mentioned, is to safeguard the so-called bulk handling facilities, and also new type of fuel will be needed for with higher enrichment, as Ajwa has said. So I think there are a lot of challenges ahead. I mean, of course, the IAEA knows how to safeguard 20% enriched fuel, or even with higher enrichment in non-nuclear weapon states, as we all know. But I really think that there are a lot of challenges ahead with the resource requirements, etc., etc. So if there are no further questions from the audience, I would like to say a big thank you to our two panelists on this interesting topic. And I think we will all have an opportunity to observe the development, how this will develop in the future, both from the SMR deployment, how many of those 100 options will eventually be deployed and where, and also how the IAEA will respond to those requirements. And I find it very important that the IAEA talks to the vendors of such facilities so that they become knowledgeable and aware of the requirements that are related to safeguards, and of course working together with the other two S's. So let me say a big thank you and applause to the two panelists, and thank you for allocating your time and for being here today. And we can see the applause from the audience. So thank you very much, and I wish you both all the best, and I hope we will interact on another occasion, Jeremy, with Ajwa anyway. All the best.
I would like to thank Ajoa and Win for the invitation.
Thank you, Jeremy, and thank you also for your support.
Yes.
All the best. Thank you. Bye-bye.
Bye.
Bye.